So Vapnik had the chance to work with this, only with this guy here, only with the possibility of selecting a function. So his basic idea was I could come up with some sort of transformation on top of this law of large numbers using in my problem, basically. And he did that. He rewrote this formulation like this. That was his first step. Remember, this C value has to be in 0, 1, otherwise we don't have a solution. That's a problem because people forget that many times. So from this, he decided to write this. I could just substitute the empirical risk of a function f minus the expected risk of the same function and somehow ensure this. And this is valid since we have empirical risks and expected risk in interval 0. So if we consider 1 minus accuracy, for example, that's the type of risk we are talking about here. It's the same as computing accuracy and do like 1 minus accuracy, that's a risk. That's our error. Basically, that's what he's doing here. So this is ensured just for a single function, and that function, remember, this function cannot be selected from data. Cannot be selected. Let me write cannot be selected from data. This is directly valid because that's just an application of the law of large numbers. But that's the case for a single function. For example, a single linear function, a single hyperplane shattering the space, somehow dividing the space. But that function could not be selected based on data. So how can I learn something if I cannot select that function, right? Based on data. That was the problem he had. So basically he decided to do this. He came up with this representation of a space of functions. He called f all, or the space with all possible functions for a problem, for any problem. That's a space containing any function we know or we don't know. Could be like hyperbolic tangents, could be sinusoidal functions, could be linear, non-linear, whatever function you think, it should be here, somehow. When we decide to select an algorithm, for example, perceptron, when we select the perceptron, we are selecting a bias here. This is the bias. He decided to call this bias as f contained, or maybe equal, depending on the situation, into FO. That's a bias. So think a little bit about this. So if I decide to select the perceptron, I could actually, during the learning process, I could select any function that's inside this bias because it's got like all linear functions in here. Okay, the perceptron is building up like a hyperplane. If I change a little, it's another function, another function, another function, another function, and that goes on. So I could have any function here. And his basic idea behind that was, okay, if I can have any function inside this bias, at the worst case scenario, I would have like so many terms like that, right? And that was his basic idea. He decided to rewrite this formulation here like this. So he knew he could do this for a single function which were not selected based on data, and that was still valid in terms of the Chernoff bound. The Chernoff bound, that for the empirical risk and for the real risk, or the expected, people call real risk, in interval 0. So from that, he said, okay, I cannot define like a single function. I cannot assess the best function algorithm selected from data, because that's just impossible. That's going to be invalid. But I can say somehow that we've got all possible cases. We've got, since function f1, the divergence in between the function, the empirical risk of the function f1 in terms of its expected risk, or the empirical risk of the second function f2 in terms of its expected risk, and so on, until reaching up a function fm. And it's so interesting. His idea was amazing, but people could say, okay, but don't you have like infinite functions inside that bias? That's a problem he left like for a while, and then he got back to that problem afterwards. So he just came up with this idea of having a finite number of functions inside that bias. If he had a finite number of functions inside that bias, consider some of those functions are the same, because that's possible. I could have like f1 and fk, which are similar, and produce the same result, produce the same risk, the same empirical and the same expected risk. And that would be the same as having some sort of intersection in between functions. I could have like a function f1 could be somehow similar to f2, but f3 is different, for example. So in terms of probability, that's obvious, because if I have a probability of one term or another, that's upper limited by the sum of those probabilities. Is that natural for you guys? Because that's the same as summing up the areas, and I'm summing up in the worst case scenario. I'm duplicating the intersections when I do that, because I'm summing up this area and this area. Of course, I'm summing up twice this intersection, and summing up this guy, and that's going to be an upper limit, of course. That's going to be an upper limit from 1 to m. In that case, because I'm considering m classifiers here, for the probability of empirical risk fi and the expected risk of fi given some epsilon. That's what he came with after some time. I don't know how many years, but yeah, he took like lots of years to come up with that kind of formulation. Yeah, that's true. Yeah, it's sad, but it's true. We should be like thanking him, not laughing at him. No, just kidding. Of course, yeah, just kidding. But from that, he said, okay, if I can sum up the terms on one side, this is the same as looking back at this formulation as a linear system. If I can sum up on one side, I can sum up on the other side. That's natural. It's a linear system. It's like having a set of equations in a matrix. If I sum up one side, I can sum up on the other side. So if I have this sum from 1 to m on one side for the probability of the empirical risk of fi and the expected risk of fi be greater than or equal to epsilon, for every function, every single function we have here, we have that upper bound. So of course, I could upper limit that by a sum from 1 to m of 2 times the exponential value of this. Of course, if I have an empirical risk and an expected risk in interval 0, 1. That's quite easy, right? That's natural. Now it's easy. Now it's natural. At that time, it wasn't. Like, it took years to define that, to prove, basically. So, of course, if we have like a sum like that, and all terms are equal, these end up to be 2 times m times the exponential value of that. And this guy here, this m guy, is known as the, what's the name of this guy? The shattering coefficient. That's called the shattering coefficient. And what's the shattering coefficient? The simplest definition we have for the shattering coefficient is the number of distinct classifications we can have there. The maximum number of distinct classifications we can have for a sample with 1 example, 2 examples, 3 examples, 4 examples. So it's a function. It's not just like a number. Some people believe this is the same as the Vapnik-Chervonex dimension, but it's not. Actually, the Vapnik-Chervonex dimension is just 1 point on that function. But that's a function. That's a growth function. A function that increases as n increases. And that's something we're going to see soon. But basically, he ends up having an upper limit to ensure learning. So just to start, suppose this guy is equals to 1, it's going to converge. As you guys saw, like when I was plotting, it's going to converge. But suppose this guy is not equals to 1, but it's different. Suppose this guy is like infinite. It's impossible. Because if it's infinite, it's going to be undefined, so we don't have an upper limit. So somehow I have to find a way of defining m. And that was something that Vapnik did afterwards. So he came up with this idea of defining m, or the shattering coefficient, in terms of sample sizes. Sample sizes. His idea was that in my opinion, that's like the most important, the most relevant contribution in the sense of practical problems. Because from that we can see how that's going to work in practice. Can I clean up? Yes. Okay. Pictures. So he came up with this idea of defining m. Okay, yeah. So he came up with this idea of defining m. And his idea was like this. Let's see. Now it's not the law of large numbers anymore. So he came up with this idea. Okay, I have the sum from 1 to m of the probability of Fi, minus the expected risk of Fi limited, upper limited by, oops, this is not necessary anymore, because now we can represent like F2 times m, 2 times n times the exponential value of minus 2n epsilon squared. Again, just to avoid the risk, because we're talking about risks, this is valid only if these guys are in the interval 0. Otherwise, you have to use the Hoffding bound, which provides like some sort of variation for us. That's also possible, because we can, yeah, it's possible, but maybe not necessary now. And from that, Vapnik decided, okay, somehow I have to find out m. How can I find m? And his idea was so simple at the beginning. It was like this. If I have this space, this bidimensional space, with an attribute x1 and another attribute x2, for example. Both are real lines, and I have a single point here. How many different classifications can I provide for that point, considering the point, only the point? 2. Because either the hyperplane cuts in here, for example, or the hyperplane cuts there. If the hyperplane cuts in here, let's say I'm going to say that point's negative. If it cuts in here, I'm going to say it's positive. Something else. What if the hyperplane is like this? Same result. So he came up with this idea of similar functions or functions that produce the same result. So if I build up, besides we have like infinite functions laying on this side, all of them produce the same result. All of them end up producing the same result. So I could say, no, not me, but he said, they are similar among themselves. They produce the same result. In terms of empirical and expected risks, they are the same. They produce the same result. So somehow he came up with this idea of translating an infinite space of functions to a finite and countable space of functions. That's the point. So from that, he said, okay, so what's going to be my shattering coefficient? It is going to vary according to n. So if I have n equals 1, it's going to be 2 in that situation, having a single hyperplane. If I have more hyperplanes, I can, of course, my shattering is going to be different. Of course, if I have 2 points, what's going to be the solution for 2 points? It's going to be 4. Because I can cut here and say everything's positive, everything is negative, one is positive and one negative, and I can say the opposite. One is positive and another is negative. So I have 4 solutions, 4 possible classifications. What if I have 3 points, 3 collinear points? That's an interesting situation. 6. 6, yeah. 6, en français, oui. 6, yes. What if, and that's something very interesting, collinearity is unstable. This is very interesting. Collinearity is always unstable, because if I bring up any kind of perturbation, what's going to happen? One of these points could change the place. And Vapnik considered that all data sets, all input spaces were unstable, because that brings the worst case scenario. In that situation, how many different classifications will I have? Everything positive, everything negative. Positive, negative. The opposite, negative, positive. We have 4 so far. Positive, negative. Negative, positive. 6. Positive, negative. Negative, positive. We have 8. So he came up, okay, so if we have 3 points in an unstable configuration, we have 8 possibilities, 8 classification possibilities. So now, with 4 points, how many we have? And that's an unstable configuration. Because every time I have a circular configuration, it's unstable. It's also called in math a generalized configuration of points. So what's the result for 4 points? It's not 16. It's going to be 14. So for 4 points, somehow I don't reach up 16, I reach 14. Why that happens? Because the space brings limitation, right? If we are working with a bidimensional space, I'm bounded by the conditions of that bidimensional space. And I cannot reach up 2 powered to n. 2 powered to n was found for 1, 2, and 3. 2 powered to 1 is 2. 2 powered to 2 is 4. Powered to 3 is 8. But powered to 4 should be 16, but it's not. In that situation, it's impossible, because the space does not provide the ability to cut the space in more ways. And you know what's the Vapnik-Chervonex dimension? The Vapnik-Chervonex dimension is always this point for which I have the greatest value for n that provides 2 power to n as scattering. That's easy to know, right? Because if I try to apply, okay, n equals 1, n equals 2, equals 3, up to 3 I was capable of producing 2 power to n. But afterwards, we start having some sort of polynomial behavior. It's not anymore exponential. It starts behaving in a polynomial way. That's why I try to draw like that. Let's draw like this to make it very polynomial. At least compared to that exponential function, it should be like, should look polynomial now. So beyond that point, beyond 3 examples, we start having some sort of bound brought by the space. So the space is limiting our class of functions. The space is somehow limiting the number of possibilities we can build up, the number of classification outputs we can build up. That's so interesting. That's a bias. And you know what this function is about? This is n. So now you guys see that n is not like a constant n, but should be m of n. It shouldn't be like m only. It should be n of n. Because that's a function in terms of n. It's not a constant. Some people just decide to employ the Vapnik-Chervonex dimension here, like 3, and people believe, I'm so happy now, because now I have a nice result. No, you are so wrong. You don't have a nice result. You are making a huge mistake, because that's a function. And this function characterizes the bias. You know what's interesting? It's impossible to tell, at least until now, how big this space was. This space, for example, F contained or equal to FO, considering this space is like the space considering a single hyperplane, what's the same as the perceptron, right? But if we use the scattering coefficient, we have a clue about that space. We know how that space behaves as we have a greater sample, as we consider more examples. And I ask you, what's the behavior of that scattering coefficient for this R2 input space? Do you have a clue about that number for that space? If you guess it, if you use a computer to estimate it, it's going to be something close to a coefficient n squared. It's going to be something close to this. So if the space is like R3, it's going to be something close to a times n powered to 3. So if it's R4, n to the 4. If it's R1000, if it's deep learning, it's going to be n to an amazing number. And that's going to bring complexity. That's going to make this space not that small anymore, but instead of that, it's going to bring a huge space. Because I'm adding complexity, basically. I'm adding up complexity somehow. So every time I consider more and more hyperplanes, I consider a greater complexity, basically. I'm not going to consider more than a single hyperplane now, because I think, I think we should go directly to what's interesting now. And what's interesting is, try now to apply this guy in the place of M. So that's what Vapnik did. Botnik said, okay, so if I have a way of computing that, or maybe estimating that, because I mean, until now we don't have an exact way of computing the sheltering coefficient, but we can estimate it. So with that estimation, we have 2 times m, which what's our m in this situation? It's something like 2a times n to the square times the exponential value of this guy. If I call this guy as delta, for example, and I solve it, I have this result, right? Take a look. 2a. I can plug this guy inside exponential, and that's by using exponential and log, right? Could have like an exponential of a log function of n to the square times the exponential of this guy. That's going to be 2a, the exponential value of the sum, right? The sum of terms, so log n squared plus, minus this guy. So in this situation, we have something like this, right? 2a exponential. This could be plug in front of the log, right? That's a basic log property, right? And this is amazing because now I can see I have a logarithm function and I have a linear but negative function. Who is gonna domain the process? The negative term. So this guy is gonna converge somehow. It's gonna take some time. It's gonna be something like this. It's gonna go up and then it's gonna converge somehow. And you know why that's so interesting? Let's see here. Let's plot to see what's happening. For example, if I have a sample size like 1,000 examples, let's say a is equal to 1, so I'm going to have 2 times 1 times the exponential of 2 times the log of n minus 2 times n times some epsilon. And you guys select the epsilon. Yeah, it could be anything. Could be any kind of, this is going to be a delta, as I called, right? So let's say the epsilon is equal to 0.1, and I run this guy. This is the convergence we have for the perceptron. So if I plot delta, I have the convergence guarantees for the perceptron. So now, somehow, I could plot close to the interval 0, 1, because this is a probability, so it doesn't happen beyond 1, right? And I could see that if I take an input sample with 800 examples, I would have a theoretical guarantee around 0.18, I don't know, 0.18, something like that. If I decide to take an input sample with 1,000 examples, I have a better guarantee. And you see, that's for a single hyperplane in R2. If I have more hyperplanes, that's going to be worse. That's going to be worse. If I have a greater space, that's going to be even worse. For example, if I consider another epsilon, for example, now let's consider epsilon is going to be, I will be like more lenient. I will accept an error smaller than 0.2 because I'm happy with 0.2 because I don't like, I'm not that, that picky with people, so I decided to use 0.2. And I try to use again, take a look. Okay, I computed. If I plot this guy, maybe using lines now, I think that's better. If I use lines in red, I will see that that's gonna need less examples because I accept a greater divergence, a greater difference in between risks, right? What if I decide to use an epsilon very small? That's a problem. Because now, if I compute delta and I try to plot it, it's just impossible to see. Because it's out of my chart. I need to have like a very, very, very big input space, a training sample. So behind that, the most important piece of information is we can theoretically define the best or the ideal sample size for any kind of problem, as far as we can estimate the shattering coefficient. And the shattering coefficient is not too difficult to estimate. It's difficult to compute it exactly. So maybe next Friday, we could estimate the coefficient, and I can I have also some. We've been working on some results, right, to bring up the exact proof for the shattering coefficient for some scenarios, not for any algorithm, but for decision trees, for example. And yeah, that's possible. It's hard to have a general enough solution for any algorithm because algorithms consider different biases. And of course, every time you have a different bias, you have a different set of functions, a different way of cutting, of shattering the space. And that brings up complexity. So after that, I was planning to go to the structural risk and formalize all the steps to find the structural risk. And the structural risk looks like people say, oh, that's difficult to use, whatever. But in practice, it's so easy to use. It's amazingly easy to use in practice to have like useful results from experiments. And probably you guys, there's something else I'm gonna add up later, which is from that I will go to the symmetrization lemma, because the symmetrization lemma will bring the possibility of computing this guy. Because we don't have access to this guy, but there's a way of computing it or estimating it in a different fashion. That's what we're gonna do. And that's very nice because that's a way of connecting, especially connecting supervised to unsupervised learning. That's interesting. So yeah, I think that's all for today. Yeah, because we don't. If you have questions, I think we could just and then we. He's worried about